Let me first introduce myself. I'm Bolei Zhou. So I'm an assistant professor at the computer science department, UCLA. So I joined UCLA early this year. So before that, I was a faculty member with the Chinese University of Hong Kong. So I got my PhD from MIT in 2018. So my research is on computer vision and machine learning. So I've done many different works from visual scene understanding to recent generative modeling and machine autonomy. So today I would like to share with you some of my thoughts on human AI interaction. And so I think that is a very interesting topic, especially for this kind of topic can be done in a research lab versus these companies. So nowadays, we see many real-world applications of AI and computer vision, from self-driving to whole robots to healthcare. So in different AI applications, so you can notice that there are always two counterparties. For example, in self-driving, we have the driver and the autopilot AI system. In the whole robots, we have the elder people and also the robots. Also for this healthcare medical decision making, we have the physician, human doctor. We also have the medical AI. So in this real world applications, so we always have the two counterparties, human and AI models. So I think it's very important to build trustworthy interactions between humans and AI. We really want to use and deploy those AI models in reality. On the other hand, AI is also achieving the human level and the superhuman performance from image classification. So we are using deeper and larger network to improve the performance. And also for image generation, so we have this GAN model as well as recent diffusion model that can synthesize photorealistic images. Also in many machine autonomy applications, such as this very complex strategic games. So those AI model trained from reinforcement learning can outperform human best players. Also, we have the AIs that can steer the vehicles in real world. So this kind of superhuman performers actually generates narrative or superhuman AI taking over humans. So people start worrying about these machines will take over a lot of human job opportunities. Also, we may create some this monster AI that may threaten the humankind. So here I would like to argue that our relations with AI models shouldn't be always adversarial or competitors. Right, so we are the creators of the AI models, and we are also the user of those AI models. So we want those AI model can better empower us and augment our human capabilities and offer more possibilities for us. So think about the inventions we have. For example, the airplane. So we invented this airplane that can help us reach the destinations faster and in a safer way. Also, for this invention of telescope, so we use this telescope to observe the things we cannot observe before. So that's why I think it's very important to make the AI models as a human-centric. So the human-centric AI is more like a reframing the relations between AI and the humans. So in this computer vision field, so I think people care about performers of the AI model. So we spent a lot of efforts that try to develop better AI models to crush the benchmarks. So at the center of the development, so the algorithm is the center. Then all our researchers try to develop deeper and larger models to crush the benchmarks. But if we shift this perspective from algorithm-centric to human-centric, it puts humans at the center of all the research and the developments. So then we can ask more interesting questions and more practical, useful questions, such as how AI algorithm can better serve humans and make our life easier. So for this kind of human-centric AI, So one very important concept is this human control versus AI autonomy, right? So you may wonder this relations between human control and the autonomy is sort of binary relations. So if we want to have high human control, then we may have low AI autonomy. So if we want to have high AI autonomy, then we may have very low human control on that. But I will argue that the relations between the human control and the autonomy and not necessarily being the binary relations. So we can have actually two dimensions to represent the relations. So here I show you a plot. The horizontal axis is the machine autonomy. So we have low and high machine autonomy, and vertical axis is a high human control and the low human control. So let's say our ultimate goal is to build reliable, safe, and trustworthy AI systems. So it's at the upper right corners. So we want to go through that directions. So there are actually already some human inventions in that domain that have high machine autonomy as well as high human control. For example, the elevators and the digital cameras. So we have many settings. We can customize the machines as we want, and then we can click a button, then this elevator will send us to the floor we want to go, or this digital camera can take a photo for us. For the another hand is the high human control and the low machine autonomy. We also have such human inventions, such as bicycles and the pianos, right? So they are have no machine autonomy, so human have to be there, but human have to spend years of practice, then they can master those skills and enjoy interacting with these machines. We also have this low human control and high machine autonomy inventions. For example, we can have this airbag and pacemakers. So those inventions, so as ordinary time, so we are not aware of their existence. Only when something happens, then some accident happens, there this airbag will engage. Then so it works in a fully autonomy way, but with low human control. We also have this low human control and the no machine autonomy, such as music box and the night mice. So I will argue that so our goal should go from the current AI system that have medium machine autonomy and no human control towards the upper right corners towards this reliable, safe, and trustworthy AI system. So there are two ways we can go there. So one is we can spend a lot of efforts to pushing this AI system horizontally. So that the efforts we pay to develop new AI models and algorithms which higher performers on the benchmark. I think we also need to pay effort of developing this human controllable and the human interactive AI. So we will do the efforts toward this vertical axis can finally lead us to our goal that build a reliable, safe, and trustworthy AI system. So in this lecture, I will give you several examples, like how can we build this trustworthy and relations with between the human and AI. So in different computer vision tasks, from the image classification to image generation to recent this machine autonomy embodied AI applications. So here I would like to think on those AI models used in different computer vision tasks as some paths. So we may have this human AI interaction. So I will make this analogy to this human-dog interaction. So those models we trained are more like our pet, right? So we train them well, then this dog can do a lot of tricks, can listen to your orders, like sit and down, and then you can fetch the object you want. But sometimes this dog will also don't want to obey your orders. So then some troubles and making mistakes. So we have to give them guidance on how to do that. Also, sometimes we may have to babysit this AI model we have to improve their capabilities. So here, the first part is the classification models. So people train a lot of image classification models. So we want to build the relations with our AI models. So the most popular ways is this model interpretability and explainability, right? So it's a rising topic in this field. So we humans want to understand what's going on inside the neural network we trained and why this neural network give us a prediction. So Ruth Fong will give us a lecture in the following talks. So I want to talk more on this topic. But on this image classification, I think another very important topic besides the interpretability is this AI-assisted decision making. So here is the work published at Nature Medicine. So it tried to examine the different AI models and how those medical AI models can be used in this clinical experiment to help the human doctor make decisions. So they take this AI model trained for skin cancer recognition and see how these human doctors can use this AI model to make an informative decision. So they discovered that when using these AI models in this human decision making, so human doctors can make more informative decisions for our patients. So I think that kind of human AI interaction for medical decision making will be a very important future direction, because we cannot totally replace our human doctor medical experts. So we have to build this human AI in the loop, human decision making. So that is the part for image classification. Then we'll take shift to the second part is image generation. So how can we build relations with the generative AI models? So generative AIs is a hot topic, especially in recent 2 years. So we have this style gun that can generate realistic images. So for this style gun models, so when we train on large number of images, then this model can take input vectors, then it can generate a lot of realistic images. So the results, image quality are very good. But the question here is how humans can use the generative AIs to edit and create our own images. That's what we care about. It's not about how good this AI models can create the image. So we care about how this generative AI can use in this content creation and content editing applications. So for example, here we want to have AI assisted content editing. For example, we want to use the GAN model to edit my own image. So we develop some GAN inversion methods that we can copy and paste my face on the celebrities. Then we are doing some diffusion process, then we can put my face inside. So that lead to problem called GAN inversion in this field. So here is a survey paper we write on this GAN inversion. So because the GAN, after your training, so you have the generator, then you can generate a realistic image. So if we want to edit our own image, so we have to do this optimization proper by giving this real image. How can we recover this latent code? Then can reconstruct the image using the generators. Then we can do a lot of latent manipulations. Then we can change the attributes of the output. So we humans want to change certain attributes. So people develop different methods such as interface scan, GAN steerability, and high GAN and CBOT. So different methods that they want to do this kind of latent manipulation. So basically, they discover these latent boundaries correspond to certain human understandable concept. Then we can add those vectors on top of the original latent vector. Then we can edit the attributes we want. But the one limitation for this kind of latent manipulation is that for each attribute, we have to train this latent boundaries. So to address this issue, so researchers come up with different ways to input our human intentions. For example, here I list the two work. One is a style clip, another one is a diffusion clip. Those models try to combine this image language model, clip model, with this image generators. So in that sense, when people input some text, then this text will be turned into some latent vectors by these clip models. Then this information can be input into the generators. Then we can control this generation process. So this text-guided image generation allow people have better control on this generation process. Another huge progress is recent this OpenAI DALLE 2 text-to-image models. So in that sense, the human intent can be conveyed through the sentence descriptions. So because human use sentence to describe a lot of things. For example, here we can input the sentence, an astronaut riding a horse in a realistic style. Then this DALLE 2 will translate the sentence into a certain image. So if we change the input sentence, then this DALLE 2 will output a different image. So here the input is an astronaut riding a horse as a pencil drawing. So it will change the style of the content. But one issue is that you can see the content still change, not like we are doing cell transfer. So the overall content already changed when we have a different input. So you can also change another input, an astronaut playing basketball with cats in space in watercolor style, then can generate this very beautiful watercolor style image. So this kind of text-guided image generation really allow human to input their intent to the generative model using the text. So the DALLE 2 models is a combination of several large-scale AI models. It's a combination of the clip and the diffusion model, as well as the most important is the huge amount of text image pairs. So it contains more than 250 million image text pairs. Then after the trainings, then people can input any sentence, then recreate the image. Despite all those amazing synthesized performance, there are still some limitations from the perspective of human controllability for the diffusion model. So if you take a look at the diffusion model, so it's an iterative process. So each time it will add some noise, it will be noise from the spatial image, and gradually you can create the contents. So the generation process is considered as a noising process, but the issue is for this iterative process, it's really difficult to control the contents. Let's say we want to change the view of the image or change a certain attribute, like global attribute, like the lighting or the age, gender of the person, so it's really hard to implement that. So to improve this controllability, so people develop some classifier-guided diffusion sampling. So what they are doing is that they introduce some classifiers on those noisy images in the intermediate generation steps. So they input the generated noisy image into the classifier, then use gradients of the classifier to guide it, the generation process. So on the right, I show you some images that generated using this classifier guided diffusion sampling on an unlabeled diffusion models. You can generate very nice images for certain categories we want. So for image generation, so we have many other ways to convey the human intent to the generative model. So people have developed the Gaussian that we can input the semantic mask to generate the things we want. Also, we can use a stroke and a brush to input our human intentions. Also, people use the sketch to express our ideas to the model. So I think that is a very interesting direction. How can we develop different flexible way to input our human intent to the generative model? So ask the generative model to generate the things we want. So here is the recent work we have doing for this. So we want to have more spatial control on this image generation process. So previously, this generator will take a latent code and then generate the image. But sometimes we may want different spatial locations of the foreground. For example, we want this output cat move its head a little bit up. Also, we may want this cat to move its head on the right. So current generator doesn't support this kind of spatial control for this image generation. So we developed some work that use to introduce some spatial control on the generator. So we follow some self-supervision of spatial key points in the generator. So basically, we design some spatial inductive files in the generator that can learn to associate with certain activations in the generator. So the issue is how can we create the supervision? So here we utilize the discriminator, because the discriminator after training, so it contains a lot of class-specific information. So there is a tension map inside this discriminator. Then we can use this emergent class attention map to as a supervision to train this spatial key point we have. So we create this self-supervision loop. Then we can train this spatial inductive files. So after trainings, then we can have this kind of interface. So user can have this use mouse to move around the key points. Then we can change the locations of the cats. And this kind of spatial control can happen at the different levels. We have 3 levels. So here is the intermediate level. So we have this more fine-grained control on this generation. So here is even more fine-grained control on that. So this kind of spatial control allow us to have to move this object inside the image around. So here's another, we add this spatial control for building generators. So we can move around, user can move around these buildings and change different parts of this object. So then we can keep overall content the same. So this kind of introduction of interaction into generative model allow us to create the content we want. So this kind of generative model can become more playable. So here I show you a work from Snap. So they built some playable environments on top of the NeRF model they train. Because in the video, so you can collect a lot of videos, then you can train some video generation model. So if we can condition on this video frame generation on the human actions, then we can actually make this generative model and generate the videos that can be controlled by our humans. So here, human can actually click the buttons, then we can control the players in this generations and make it more like an interactive and playable environment. So that is also a very interesting direction to make our generative model more interactive. So that is the second part for this to add this image controllabilities for this generative model. So the third part I will talk about is this how can we build human AI interaction for this AI model trained for this machine autonomy applications. Because nowadays, so there are a lot of excitement in this embodied AI. So we train this embodied AI to accomplish a lot of tasks. For example, we can train some driving policy to drive inside the environment. We also can train some reinforcement learning agent that can navigate inside this indoor whole environment. So they can navigate to certain locations. So here I try to train some this embodied AI model, try to learn a visuomotor driving policy using this very popular learning algorithm. So it's a reinforcement learning algorithm. So it just build some interactive environments, then we can train this agent. But one issue with reinforcement learning is that there is no safety guarantees. So you can see here is a training agent. So just doing all kinds of crazy things inside the environment and cause a lot of troubles. So for this kind of embodied AI agents, of course, we cannot deploy and train this model in the real world. So we want to improve the safety and the reliabilities of this embodied AI models. So what we can do is that we can also build this human AI interaction. So we can have this human in the loop learning with the safety guarantees. So for this kind of agent and environment interaction, besides the agent and environment, we also can include the human in this loop. So originally, this reinforcement learning only have this iterative interaction between the learning agent and this environment. So there is no safety guarantee. So right now we include human in this learning loop. Then this human subject can help us to safeguard this active exploration of the learner. So you can think about this human as a parent or some guardians that can supervise this the exploration of the kids. Then whenever some accident or danger will happen, then they will actively involve, and then they will demonstrate the correct actions when something is going to happen. So this kind of human in the loop learning method is very important for this kind of real world applications of embodied AI. So here is the work we have done published at ICOR this year. So we have this real human in the loop. So here is my grad student. So he is training this agent, monitoring this training process. So at the beginning, so this agent has some explorations. So if this agent running into some trouble, then this human subject will involve and participate in this learning process and take over the control. Then it will show the correct action to the agent. So in that case, so we can ensure the safety of the exploration process. So here you can see, so we speed up after about 20 minutes of training. So this agent already can do something. So without the intervention of the humans, so it can navigate inside the environment, not so confident, but still can do some tasks by itself. So here is another one. We also tested this kind of human in the loop learning in the color environments. So we built this human interface. So human can monitor this model training. So whenever this agent run into some trouble, then the human will take over. So after several minutes, so this agent already know to drive in this straight road, just several minutes. But still running into the trouble when trying to turning left. So human will involve into this process, and will continue to demonstrate this learning process. So after about 10 minutes, then this agent already know how to drive inside this color environment without the human intervention. So that is very interesting, because in this work, we even don't have any manual design for the reward function. So if you have any experience in reinforcement learning, so you will know this reward engineering, the very important thing in reinforcement learning. So here we just use the intervention as a supervision signal to train our agents to try to minimize this intervention from human beings. Then this agent will know how to do this task. So also there are some other work inside this embodied AI research. So here is the work I highlight from MIT. So they developed some environment for virtual hole. So they built this kind of watch and help. So it's a task that human will collaborate with this trained agent to accomplish certain tasks, like try to search for some object. Then the human will control some agent, then will collaborate with another agent controlled by the AI, and to accomplish the task. So this kind of human AI collaboration is also very important future directions. Think about that. We have more AI models deployed in the real world. So we want better collaborate with the AI model to achieve certain goals. Another topic inside this embodied AI is this human AI shared autonomy. So we have done some work towards preliminary work on this direction. For reinforcement learning agents, so usually people just train this agent to accomplish this primary task. For example, for this Mojoko ant environment. So when we train this agent in the ant environment, then this after trainings, so this ant will learn how to move forward in this autonomous way. So without any human interventions. But the limitation is that this agent can only do this task autonomously. If we want this agent to do some other task, like turning left, turning right, then the agent don't know how to do it. So to enable this kind of human AI shared autonomy, so we developed some measure called policy dissection. So it's an analogy to our previous work on this network dissection or GAN dissection, that we try to interpret the internal representations of the training model. So we want to identify those emergent knowledge nerded inside the representation. So here we found out there's an internal representation actually learn a lot of this behavior functions, such as how to roll the body, how to throw the front leg, and how to prep the left leg. So after we have this kind of labels for those internal representations, so user can simply activate and deactivate certain regions, then we can achieve this kind of human machine teaming on this kind of sheer autonomy. So here is a demo video showing you that at the beginning we have this agent just moving forward. Then here, after we identify this controllable latent representations, then when user press some keys, then we will activate and deactivate certain regions. Then we can have this kind of control the behavior of this ant. So like moving left, moving right, or just stop here. So we can make this agent more controllable. So here is another environment. We deploy our methods. So here is another reinforcement learning agent trained inside this environment, just moving forward. So before the training, so this agent don't know what to do inside the. So before the training, so the agent don't know what to do. So after we training this primal task, so this agent know how to move forward, because the primary training task is just moving forward. But when we deploy this agent in some new environment, like full of obstacles, so this agent don't know how to navigate, because this reinforcement agent have very poor generalization capabilities. So after we identify these internal representations, then we can have this kind of human AI shared control. This human can just press a certain key, then we can control the behavior of this agents, like turning left and stop there and turning right, have this kind of shared control. So that will be very useful for a lot of this autonomy applications. So we can build this human priors inside the autonomy and ask the agents to listen to our high-level human orders to achieve this like a hybrid control. Okay, so that's pretty much for my lecture. So I think it's very important to have this human AI interaction. So we want to build this synergy between the machine and the human intelligence. We want to build this trustworthy relations with your AI models you have, like your pets. So here I also list a reading list about this recent progress in human AI interaction. Okay, so I will stop here. So let me know if you have any questions. Yeah.
When we're talking about diffusion, and I have been working on some interpretability and human interaction reductions recently. I'm quite interested in the two questions. The first one is, as we showed before, one class is the goal, the final goal of the human AI interaction is that we try to get a perfect model and perfectly mimic the experience of human beings. Is that correct or not? If the previous example show that there's not just only one solution for the stage for some autonomous driving, right? So if that's one question. Another one is that if the final goal is now to try to let the AI model perfectly mimic the interface, do you think it makes sense? That's just a definition I think for me. Do you think it makes sense that we involve the human beings to try to train the human beings to be familiar with how the AI model performs? I'm trying to understand the right model to make the decision instead of trying to get a perfect model to explain itself. Do you think that will also help into the work of human interaction?
Yeah, so thanks for the question. So your first question is about the primary goal of the training task aligned with the human intent. So I think that's a very important question. So that's relevant to this AI alignment problem people are talking about. Because sometimes when you design some task, you design some reward function, but it turns out this agent learns some other like short paths to accomplish tasks. So in that case, the reward function cannot correctly reflect the things we want. So I think there needs more work towards this direction, because not of the time it's very difficult to encode our human intention using some reward function or using some loss function. So I think there should be more like fine-grained supervision over this process, then we can achieve better goal for that. Another question another issue you talk about, so this AI actually can learn multiple solutions to solve the task. I think that is also a very interesting direction. So it's relevant to the diversity of the solutions. So like for our human beings, when we solve some problems, so we may come up with different solutions. But for the AI, like a reinforcement learning agents or some other like learning algorithms, so they are limited by the reward function we define. So I think that there needs more work towards this direction. Like how can we design better reward function or loss function that can parse our human intent into the learning process. The second question you talk about is about how human can learn from the AI model, or how can they adjust their behaviors, right? So I think that is also a very important point. Especially nowadays, we have a lot of more and more this superhuman AI model. They have this superhuman performers. Then I think we are at the stage to learn from the AI models to solve some problems. So that can actually improve our capabilities to solve some issues. So I think I watched some videos, like interviewed like Ke, so which is who is a top Go player, Chinese Go player. So he played with this AlphaGo, and he actually said he learned a lot by playing against this AlphaGo, and they learn a lot of creative solutions to solve the task. So I think how can we learn from AI models will be also a very important future direction for this human AI interaction. Yeah.
Hi, just to my question is about the interaction of how we can teach the AI models learn self-driving. So how efficient is the signal or the reward compared with other, if I take same cost of time to labeling some data, or yeah, this is first one. Second question is how to handle the unbalanced signal. For example, you just show up to 6 minutes to learn how those three, but it takes longer time to turn left. How to handle this?
Okay, so your first question is about the sample efficiency of the human-in-the-loop learning algorithm. So we actually found out compared to this pure reinforcement learning algorithm, so we are like 10 times, I think it's 100 times faster than this pure reinforcement learning algorithm. So it's actually quite efficient. So it's also relevant to the representation we use. So right now we are using this LiDAR, like a one LiDAR representation. We want to do this kind of generate the control signal from the visual representation, then there will be this representation learning problem. So that is another very important issue in this kind of embodied AI, like how can we learn better representations that can facilitate the final behavior, like control outputs. So I think those two parts should be coherent with each other, so we can have better representations and the sample efficiency can be greatly improved. So people can always come up with some like pre-training, like how can we pre-train this visual policy representation. So we actually have some work in this direction, like how can we NeRF some driving policy using some YouTube videos. So use this kind of pre-trainings that can give us a much better representation than this ImageNet pre-training. What's your second question?
About the unbalance.
Okay. Yeah, so the unbalance is also a very important issues for this reinforcement learning environment. So I always have this trouble with this embodied environments such as Gibson or other environments. So their environment is fixed, right? So they only have limited number of environments, and it's very easy for the agent to overfit the environment. I think recently there's some work from I think Allen Institute. They use procedure generation that they can generate more interactive environments. So in that case, we can control the distribution of the environments. Also, we can have much more diverse environments that can improve the generalization ability of the agents. Thank you.
Especially my question is, how do you quantitatively measure that a model interacts with human well? Could you please give us an example or intuition?
You mean the policy deception?
It's a general question.
Oh, general question. Yeah, so I think we will evaluate the human interaction using the number of interventions because human budget is very limited. So we have to be very careful about that. So the number of interventions and also the how comfortable human can use this interface. And we want, so one thing we found out it's very important to build an intuitive interface. Right, so because it's more like a game environment, so human want to play the game, so we want to make the game interface more intuitive, then they can better intervene this learning process. So we actually play a lot of games. My grad students play a lot of games, so they can learn this how to design better intuitive controls for this type of environment. Thank you.
Trust and explainability is often default to factors mentioned in machine collaboration or through AI interaction. Are there other things that are also important for
Yeah, I think trust is like nowadays we have a lot of this trust words machine learning to become a buzzword. Like the interpretability. So I think trust is from the understanding, and if we can better understand what's going on inside the model, then we can have better trust. So I will say the trust is more like a goal of doing all the things. So if we can improve the transparency and then improve the explainability and the interpretability of the AI models, and also we can improve the generalization of the AI models, then we can have better trust. So this also the interpretability and the explainability, so those are the different attributes, like human-centric attributes of the AI model. So of course, there are many other attributes we also care about, such as the BIOS. We want to reduce the BIOS, and also the reliability things. So there are a lot of things we should care about for this.
Thanks again for the presentation. So from the demo, you showed that human teaches the AI to drive. One consideration I found is that human cannot give some level of feedbacks to the AIs like computers. So it may not have the efficient to teach the AI by human. Is there a way to solve this?
Yeah, so that's about how can we build this mechanism about human intervention. So here right now we have this active intervention, which means the human subject will actively monitor this training process. So that gives a lot of this mental stress to our human subjects. So it's also not that efficient. So another direction to go is we can develop some uncertainty inside this learning agent. So the learning agent can learn when it cannot solve some problem, then it will ask for help from humans. So from that perspective, I think we can improve the comfort of this human intervention. But I agree with you, like how can we better design this implementation mechanism? It's still an open problem, so we still need more effort for that.
Okay, thank you.
Okay, great. So if no more questions, so thank you all for this is our first session. So the second session will start at the 4 p.m. So we still have 2 lectures. So